Okay, so what I want to say, I want to talk about
in the file system, but I think you just now can
two functions. I'll tell you what those are, and I'll just focus on low dimensions, just because that's most interesting, somehow to us. And I should, before I forget, say that this is a joint work. And somehow, you know, the phrase two functions, I think Peter Beckner really disapproved of us calling it two functions, but and probably lots of other people do too. It's not entirely our invention. But anyway, it's supposed to vaguely suggest two categories, although I don't actually know what two category is, but maybe nobody else really has decided what two category is anyway. But this is going to be like a super down-to-earth talk, and very low tech in many ways. Lots of pictures and some sense a lot of examples of low dimensional two, just to draw some pictures. I kind of want to get your intuition going more than anything else. We'll try to state some theorems at the end, but I won't start with the theorem, try to explain it. I'll try to just develop the intuition as we go, and leave you to fill in the fancy language and figure out what the two categories are if they're there at all. But somehow the idea is, so let me just tell you what a Morse 2 function is. Anyway, I will find something. So Morse 2 function, this just means a generic, but by example to show you what generic is, but generic is the same as stable. In this case, stable, smooth functions, G from some n manifold X to some two-dimensional manifold. Okay, so the 2 is about the dimension of the target space. Okay, just as ordinary Morse functions are generic and smooth functions to one dimension. Yes?
If n is larger than 0, then generic function is stable.
Yeah, the generic not being stable issue is like dimension here. I forget what it is, but it's dimension 6 in the target or something. It's just some issue that matter. That way, yeah. I mean, that's an incredibly weird phenomenon, but that's not come up here. It's just for those of you who don't know. So what stable means is you wiggle it a little bit, right? And locally, you could, if you perturb your function a little bit, then you can change your coordinates in domain and range, and it looks like nothing happens. That's what stable means, right? So, and so like a cubic, right? As a function from R to R is not stable, so you can perturb it to get two critical points or none. F cubed is not stable. Okay, so let me also just say a little bit about, so we kind of see this as what we're doing is sort of foundational for other stuff, and I'll tell you some about the motivation. But as I said, I just really want to kind of get you to understand what these things are, what they look like. Just some of the names, but I'll forget to say names as I go along. So let me try to say them now before I forget. So of course, background goes back to, well, Morse, about ordinary Morse functions, right? Morse, and then surf, we're thinking about one parameter families of Morse functions, which plays a big role in us, and then Tom and all in his school thinking about singularities, classifying singularities of smooth functions. Sort of more recently, Saeki had a nice theorem. It's about trying to take generic maps to two-sphere and make them nice and eliminate certain kinds of singularities. And then much more recently, people, Yanko and Keeley, sort of turned us on to thinking about things this way. Minaj Baikur, Jonathan Williams has some related results. And then Rob, as a student, just finishing Ka Choi, who has some examples. And then a lot of the motivation for, original motivation for this in terms of thinking about four-manifold invariants and so on is Tim Perutz's program related to Lagrangian matching invariants, which was supposed to produce four-manifold invariants out of what we call broken Lefschetz vibrations, which feeds into this story a little bit. I'm sort of just throwing a lot of words out so they can connect to something you might know or names you might know. And more recently, Tree Verhan was Franklin sort of steered us a little bit with her quilted story that you'll hear something about there. And that's probably the last, this is probably the last board on which I will mention names, and I may forget. So if you're in the audience and I'd say something and it's really due to you, well, here I mention your name here. When something is, when a result is really minor, I'll say something. Otherwise, by default, it's not hard. Okay, so just to get really basic examples of generic smooth maps, let's look at examples where n is 2 and sigma is just R2. And let me just draw a generic map for the 2 manifold of R2. Here's a sphere. And, but I'm going to do, let's see, what do I want to do? I want to settle on some color codes to begin at the beginning. So this way, what I'm drawing here is vertical slices of the sphere. So the sphere is mapped on the board, which is R2, and there's a couple of features here. The sort of silhouette of the sphere, right, is sort of, if you look at what's the singular set of this map onto the board, the set of critical points, points where the derivative does not have maximal rank, is the image of that is the circle. Okay? And then these circles I've drawn, really you should just, I've tilted them so you can see them that they're circles, but really they should be purely vertical. Those are slices. They're going to play a role in just helping visualize this. Of course, I can do much more perturbed pictures of the sphere. For example, you do something where you take a sphere, but then there's sort of a little bump that comes out in front. And if you draw sort of the singular set, you have a silhouette that sort of looks like this. And then the vertical slices on the left will still be circles. Well, they'll all be circles, but they'll look a little different. Here you have something that comes down, goes back up, down. So maybe you'll recognize this is what's called, there's a cusp here in the singular set. You can have something like that, and I can do other things. For example, I could put sphere napkin where I sort of, instead of putting this little bump in the front, I can sort of push up from below with my hand and have a vertical, still a vertical slice looks like that. These examples are going to feed into what I'm doing next. Let's see. Sort of in the back, it goes up and down and up again, and back around. Here it comes down, goes up, back. So I don't have pictures of that good, but I think you know what I'm talking about. So those are just some sort of simple examples. Let me do some just to get you thinking in the right directions. Okay, how does a sphere? How about a torus? Of course, draw a torus like that. And so now we have something happening where the topology of the vertical slices changes. And that, again, what we're going to see, zero in on this back later, is the topology of the vertical slices changes precisely when this image of the singular set is a vertical tangent in this picture. But that's not everybody. That's not everybody's favorite picture of the torus. Everybody's favorite picture of the torus is this. Right? And then you should immediately ask, well, what's really going on with this little smiley guy here? What's really happening there? Okay. But of course, you can do even more. You can also have lots of pictures of the torus. You have the torus. This. And vertical slices. This is somehow different than this one, right? Okay, so let me just tell you what's going on here, because it's sort of good for developing your intuition as well. No one ever draws what happens in the background there. So here in the background, really what's going on is this, of course, this set of critical values extends, and then how does it join up with this set of critical values? Well, it joins up like this. And you can probably believe that if you think about the example carefully. Let me show you a little bit, just even more, so to exaggerate that example a the vertical slice at either end is still just a circle. But the vertical slice here, for example, is you come down behind, then you got it, you come up, or you can see this back there, you come back down, then you come up, you can just imagine, and then there's a little doubling back there. That's it, and then somehow, so you sort of want to imagine you've got a circle here, but now in the vertical direction, you've got a Morse function on this vertical circle slice. But this Morse function has developed a pair of critical points, a pair of canceling critical points. But now this lower critical point and this higher critical point here come together and merge, and then at that point the topology of the vertical slices changes. And you get two circles. That, and then those two circles pull apart. So all of that was sort of to lead up to, I've emphasized various features, and I want to emphasize those as sort of general features of general maps to two dimensions. I guess the one thing I haven't drawn is a non-generic map to two dimensions. Of course, there are lots of such things, but it just a sort of simple one. For example, you can take a torus and map it sort of stupidly straight on, right? Torus and the map straight down, and you see two circles right on top of each other here, but of course you could, then if you perturb that a little bit, you can perturb it to something like that, where again your vertical slices. So this would be a non-generic. And there are lots of other much worse non-generic pictures you can draw. But so that's all supposed to be a setup for me telling you what the local behavior of Morse 2 functions are. And so I'll try to illustrate both when the domain of dimension is 2 and then when the dimension of the domain is higher. So make a little table. This is local behavior for Morse 2 functions. G from n manifold x to some sort of sigma, but it's just local, so really just the picture is just the target spaces is R2. Okay, so just I'll draw the pictures when n equals 2 for n on the left, and I'll write formulas for n bigger than on the right. And this is just standard stuff from singularity theory. So one of the models is you see something like this. Okay, those are such a map down to dimension 2 is called a fold. Well, the behavior near this singular set is called fold, and of course the map is, if I think of this direction as t and this direction is, well, this direction in the domain is x, and it's tx maps to t linear plus or minus x squared. Okay, and the generalization of that is that's one local model. The generalization of that is t and then x1 up to xn minus 1 maps to t and then some sum of squares, right? So minus x1, normal Morse critical point, minus xk squared plus xk plus 1 squared, xn minus 1 squared. Okay, so that's the generalization of this picture in this dimension. The point is that you know, if I were to draw a picture, you down in the range, just in a little square box in the range, you'll see the image of the singular set, the image of that pole, this horizontal line, and then the point is it really just looks like, you know, there's one dimension of the domain, which is mapped by the identity, the same dimension of the range, and then the other direction just looks like a standard Morse critical point of index k, some index. So we indicate that in our diagrams this way. So what this is really pictured here, this is I interval cross an n minus 1 dimensional can. Okay, so not really that exciting. Another way to say it is if I take, if this is the map G, then G inverse of a vertical slice here, right? G inverse of a vertical slice is an n minus 1 dimensional cobordism. Cobordism, elementary cobordism. Okay, so I fibers are codimension 2 in the domain, and then the inverse image of this vertical slice is codimension 1, and that's going to be a coordinate in and of itself. Because that's the model for a fold. Oh, the other thing to say about this, of course, is that this is just a local model. I could turn this upside down. I mean, there's no global sense in which I prefer this as up, right? And so if I think of it going the other way, then that's an n index n minus 1 minus k, not n minus k, right? Because of the fact that it's time across that. So we, sometimes draw pictures of these folds. We'll draw images of, we draw pictures in the target space where we draw the image of the singular set, and we draw the singular set consists of folds and cusps, which I'll describe next, and then we indicate the indices. But you always have to draw a transverse little arrow to show which direction in which direction you're counting the index. So then the other local model is a cusp, and so it looks in 2 dimensions. You can actually draw a picture of it, which we've already drawn. I'll draw the local picture completely. So it's like this. So you just have your piece of cloth on the table, and then it develops a ring point right there. So, and then the local model is, we've seen this already in Morse theory, is the birth of a pair of critical points, t and then x cubed, plus or minus tx, depending on whether the cusp is going one way or the other. And so this point here is called cusp. And if you actually solve, it's a good exercise to do to actually solve for the find the set of critical points and then find an equation for the graph of the image of the set of critical points, and it's a semi-cubical cusp, right? Y squared equals x cubed type of cusp. And then in higher dimensions, the only difference is that x1 and x1 maps to t minus x1 squared minus xk squared, and then at some point in the middle, say k plus 1, you put this model, k plus 1 cubed plus minus is this drawn the way I've drawn it, so minus tx plus 1, and then plus 2 squared. Okay, and so that's again the standard picture for a birth of a pair of critical points in a one-parameter family of Morse functions. And the image again is you just draw an abstract picture for higher dimensions. You're just going to draw the image of the singular set will be a cusp like this. This is a fold, so that's a cusp, and then this is a fold, and that's a fold there. There's a fold and a fold, and this is an index. If that's an index k fold, that's an index k equals 1 fold. Of course, you might have wanted to measure indices going the other way around, so then this would be n minus 1 minus k, and this would be n minus 2 minus k. Okay? But the point is, it's just I cross a birth of a k plus 1 pair of critical points, but there are n minus 1 dimensional animals. Think about its animals as well. And so there's, it's like a slogan. The slogan is that Morse 2 functions are locally time cross generic homotopy between Morse functions. But globally, there's no time. Okay, so that's the generic homotopy where nothing interesting happens. This is the generic homotopy where this is the local where the pair of critical points happens. The one other thing that I have not listed as a local behavior is where two critical points cross. So folds can cross. That's somehow partially local. It's local in the target, right? But it's not local in the domain because in the domain those are far apart, right? But that's something you want to think about as well. Is you can have what we've seen, like right here, for example. So here, folds are crossing, that can happen. Okay. Of course, you may say, what about handle slides? And that's a good thing to ask, but I don't have gradient flow lines, or I don't have gradient vector fields and so forth either, but it's still, that's a good question to have in the back of your mind. Yeah?
Just to interject, at least in the two-dimensional case, that classification you just gave is
Yeah.
1950 paper, has the weight-based.
Okay.
Which actually anticipates on, in that same paper, gives a complete proof of what's known as on-trench cell.
Oh, really? Okay, I didn't know that.
Jet on cell.
Oh, cool. Okay, good. Thanks.
This is for jet.
Yeah, so this is obviously very old stuff, and to emphasize, just to draw a quick picture that shows that you don't globally, what's happening, why you don't globally have time, of course, is, if you have what we've seen here, in there, the point is that at the left end of this picture, at times, if you want to model it by this picture, if you want to say that's a fold on the left edge, you have to run time upwards. But it's here for this cusp, you have to run time to the right. So observations here. If you like, you could take this definition of the Morse 2 function and then say you want to prove it's generic in the state. So one observation is that DG has rank 1 or 2, never 0. And I think if you never thought about this before, well, it may sort of surprise you that, for example, branch cover from 2 dimensions to 2 dimensions is not a generic smooth map. I don't know. It's not. So, for example, so z goes to z squared. It's generic in the complex sense, but not generic as a smooth map. It's not generic. So that's what happens when you have branching. Or in 4 dimensions, Lefschetz singularities, w z goes to w squared plus z squared is not generic. And I should now say that Rob and I were thinking about broken Lefschetz vibrations, which is maps to the 2-sphere, where you have Lefschetz singularities and folds, basically. So, and these were introduced by Arudons and Kansarkov in a paper that was taking near symplectic manifolds and producing things analogous to Lefschetz pencils, except that there were these extra singularities required. And Rob and I were thinking hard about this, and we were in Cape Town, and we got this email from Janke saying, because we were thinking about uniqueness, and we proved some things about existence, and we wanted to prove something about uniqueness. And Janke's, this was an early version of his thesis, I guess. And he suggested, if you're gonna, you really need to get some uniqueness statement. You really need to just say, well, I'm going to pass from here's smooth function, here's another smooth function, so I need to go just look at generic homotopy continuous functions. But the functions we were dealing with to begin with were not generic, because they had these Lefschetz singularities in them. And so he sort of said, well, it's known how to perturb these to make them generic, then see what happens in between. Anyway, we just didn't get, as many other times, sort of someone explained something to me and didn't get it, didn't see the point, kept thinking about our own thing until much later suddenly I realized that was a good idea. And so we've, in some sense, moved very far away from thinking about Lefschetz vibrations because they're not generic, but they're sort of lurking in the background in many ways as well. And in particular, it's actually well known how to perturb both of these to make them look like Morse 2 functions. In both cases, when you have an isolated critical value, isolated critical point, isolated critical value, and when you perturb it, that isolated critical value perturbs to a little triangle of folds with 3 cusps. And it's a beautiful, I mean, when I first saw this, I spent time trying to understand what was happening in this dimension, but actually it's worth just thinking about what's happening. It's really the same thing as what's going with the map, the 2 dimensions. So if you've never thought about this, it's a great mental exercise to think about just the ordinary two-fold branch cover as a map from R2 to R2, and see how to perturb it so that it's just folds and cusps. And see, you perturb it, these will be index 0 cusps in the picture a little bigger. You basically have, you're going to have the inverse integral point out here will be 2 points, and the inverse integral point in here will be 4 points, right? And there's somehow you almost ought to be able to do this with your tablecloth, except not quite, because you need to immerse something. I've never done it with a tablecloth, but I've tried. But it's sort of tantalizing because it's sort of easy and sort of hard to see that. Okay, so that's one observation. Second observation is that the index, you can talk about the index of a fold, except it's well defined up to turning things upside down. Well, it's well defined up to sort of k goes to n minus 1 minus k, right? And so you can talk about index 1 fold, but you should remember that from the other direction, say n is 4, an index 1 fold from the other side is an index 2 fold, for example. But it also hints that there's sort of special types of folds, and something that causes problems in some. So we talk about definite folds, and definite folds are folds of index 0, which is the same as n minus 1. And so that's what we've seen in not all pictures of 2 manifolds, of course. The only folds we have are index 0 or 1, which are the same. So all our folds are definite, but in higher dimensions you may or may not have definite folds. And the key thing is about definite folds that can cause problems is that they change the number of components of a fiber. Okay, the point is, in dimension 4, box, if I have an index 0 fold like that, what that means is, well, down the inverse individual point here is some fiber, some 2-dimensional fiber inside 4 manifold, and then as I cross this fold, well, this is just locally, if I just look over this vertical slice here, I'm just attaching a 3-dimensional 0 handle over that vertical slice, and then when I get to here, I have that same circuit of fibers, that original fiber disjoint union. If you like see this. Okay. So, if there are various settings in which people don't like disconnected fibers. Maybe Jake will tell you something about that, or not. Anyway, you can imagine if you're doing something, if you're trying to do some symplectic geometry or, I don't know, compute some fancy stuff associated to symplectic manifold associated with these fibers, disconnected fibers can cause all sorts of trouble. Actually, 2-sphere fibers are also kind of homologically trivial. 2-sphere fibers all by themselves are problematic. Indefinite folds, you would hope are better, right? Sorry, I didn't say. Why did I say definite? Why the word definite? Well, you write down this local model up here, right? It's just, if it's index 0 and minus 1, then you either have all minuses or all pluses in that quadrant. Okay, and so if you're anywhere other than those indices, then you have an indefinite quadratic form there, so it's an indefinite fold. So indefinite folds likely don't disconnect the fibers. Okay, except they can in certain dimensions, but so even if you somehow avoid definite folds or avoid too many definite folds, you still might have indefinite folds that disconnect the fibers for the following simple reason. So if you have, again, this is dimension n equals 4 in the domain, and this is a index 1 fold, you might have a, say, genus 2 surface as your fiber here, and then, sorry, 2, index 2 fold, so as you're going across, so if you have an index 2 fold, this is a if I take a slice here, I've got a 3-dimensional coordism, which is obtained by attaching a 3-dimensional 2 handle, so that's attached along some simple closed curve in the surface, and if it happens to be separating, then of course, you've got this fiber. Now, or going the other way, you have a pair of points that come together, and this would be index 1 fold that way. Okay? One thing that Rob and I set out to do was to try to prove theorems about existence of Morse 2 functions mapping to various surfaces without definite folds, and furthermore with connected fibers everywhere. And as you can imagine, it's a little bit subtle. So we have a variety of theorems. Basically, with all of the, if you rule out all sort of, if homotopically such a map exists, then it'll produce one. Of course, if dimension n equals 3, then you're never going to have connected fibers, because the fibers are in circles, and you're going to get lots of different components and so on. So that's dimension n equals 4 is where you start to have connectedness. And also, we set out to prove theorems about if you're going, if you have two homotopic maps to, say, S2, which have only indefinite folds and have all fibers connected, can you connect them by a generic homotopy between Morse 2 functions that preserves the property of having only indefinite folds and all connected fibers, and we can do that as well. So that's sort of, I may not even state those theorems anymore. I'll show a different theorem at the end, but that's sort of the setup. Okay, so what other observations? Yeah, so the next observation is, really should remember that. Okay, so you sat at 12:15. So the other thing that I wanted to hint at with the first pictures with just 2 manifolds was that you can map to R2, and then of course you can map R2 to R, right? And so generically, if I take G and map it, and so this goes, if I have an n manifold mapping to R2 by a Morse 2 function G, and then I map that to R by, say, the projection on the horizontal axis, generically you expect that to be on this Morse function. Okay. And what we saw was that this torus, for example, right? If you take this torus like this and you project it down to the horizontal axis, this is your usual picture, except for some reason we ended up making all our, well, we call this the horizontal Morse function associated to the map to R2, and so you have a critical point of the horizontal Morse function here, 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 critical value there, okay? And those critical values correspond to the vertical tangencies of the fold set. Okay, so you can work that out in local details. I mean, you just take all these local coordinate charts and figure it out. It's not that hard, but basically what the generic is just arranging that the folds have, at all their vertical tangencies, they're like quadratic, parabolas this way or that way. Okay, and then so this is the Morse function, and the critical points correspond to the vertical tangencies of the fold set, of the image of G of codes. Of course, you could have chosen to project a different way, and then you have different critical values. Oh, you know, there's a group of names that I did forget to mention here, which is, and I didn't know about this until recently, although I should have. There are people in Freedman topology who thought about stable maps to 2 dimensions. In particular, Rubenstein and Charlemagne, right, and Jesse Johnson, and I don't know how many people here know this, but and there's, you know, if you want to go between, if you want to think about going between 2 different Morse functions, how to get a homotopy from one Morse function to another, what you could do is say, let me take those 2 Morse functions, let me make a Morse 2 function out of it, assuming they're suitably generic. Let me map, one of them's going to be mapped to X, the other one's going to be mapped to Y, right? And then, assuming that they behave nicely, they're generic with respect to each other, I'll get a Morse 2 function. And now I can get a nice homotopy from the projection in the horizontal direction to the projection in the vertical direction by just rotating this. Okay? And it's a great exercise if you're teaching about Morse theory to grad students. And you know, one of my grad students will not be able to do this. To sort of draw your favorite picture of a surface and then have them, you know, just spin it in 3 dimensions and look at the surf graphic you get. You know, the homotopy of Morse function. But they were able to suggest to Johnson and come following ideas from Rubenstein and Charlemagne, and probably many other people in the field were able to prove results about, you know, how many births and deaths of critical points and so on you will get in between going from one Hayward splitting to another this way. I'm far from an expert in that. I just realized that I probably should have known about that long ago. They use exactly this point, and of course, you know, you'll have a birth of a if you're going to rotate this and see when you get a birth of a pair of critical points, it's going to be exactly sort of an inflection point in the fold set. Okay, so. So higher dimensions mean what happens is if you have an index k fold that has a vertical tendency like this and you project down, that'll give you an index k critical point of the horizontal dimension. You could think for yourself, what if you have this index k, what's the index of the projection down to the horizontal direction? And that's not going to figure out that. So then the last sort of, piece in here is, what about in between? So, 6, observation number 6, in between these vertical tendencies, what's happening? Well, in between the vertical tendencies, you have the topology of the vertical slices is not changing, right? Here, the topology of the vertical slice changed between the vertical tendency, and then in between those, the topology isn't changing. Of course, it's not, because there's no critical points of the projection to the horizontal direction, and so you can parameterize everything in between 2 vertical tendencies as codimension 1 manifold cross I, right? And then you can just say that you can think about projection to the vertical direction as a 1-parameter family of Morse functions on the vertical slice. Okay, so in between you get you know, basically G is really T comma P maps to T comma G sub T of P, where G sub T of P, G sub T is a from some n-1 manifold to R, is a 1-parameter family of functions, and it'll be generic as well. So that's what surf theory studies. Okay. Okay. So. I want to draw a big picture for that. So you can have all sorts of things happening. Maybe I will draw one picture there. Yeah. So the last, in some sense, what I'm leading you up to is how to build your own Morse 2 function if you want to make one. So you want to be able to put these pieces together. So, again, let's just go back to draw. I had a more complicated picture I wanted to draw, but just take more time to confuse you more than anything else. So let's just keep it simple. So I go back to this picture of the torus, and here's a zero handle. Right? As I move from, so I'm thinking about the map from the torus down to the plane, and then from the plane down the horizontal direction. So I have my usual 4 critical points. So there's my 0 handle, 1 handle. This is a 1 handle also, right? And this is a 2 handle. So going from the left to the right, if I focus on that 1 handle, where is its descending manifold? Its descending manifold, of course, its descending manifold, probably that color, descending manifold, goes like that. And where does its descending manifold land? It lands, of course, in a vertical slice as a pair of points. This is I'm just going to extrapolate straight from this dimension to high dimensions, but you'll understand. And where's the handle? The handle is there. So what I want you to get out of this is that the attaching sphere for this 1 handle lies, of course it lies in the vertical slice, but not only does it lie in the vertical slice, it lies in a level set of the vertical Morse function on the vertical slice. Okay? And furthermore, it's got a framing which is compatible with that level set. Okay? So the more generally, if I have this picture, this gives a K handle, an n-dimensional. So n-dimensional K handle attached along, let's say, K-1 sphere, which is contained in, it's contained in see here, I tilted everything so you can see it, but really it's contained in a single fiber, contained in a fiber of G. But of course, a fiber of G is really a level set of this G sub T, which is this vertical Morse function. You have in between here and here, there's 1 parameter family Morse functions, and it's contained in a level set of the vertical Morse functions. So G sub T is a map from, what is it a map from? If I call this, I'm thinking this is T and this is Z. It's our usual convention coordinates. So it's G sub T maps from capital G inverse of T cross R, right? And so it lies in a level set, and then if you want to pay close attention to framings, with the framing compatible with that level set, which means, in other words, the normal bundle is split by this Morse function, so on, that framing should be compatible with that. So that's the. So maybe I'll say something rather than write it. The idea is, suppose you have an n manifold and you want to build a Morse 2 function. You want to build, let's say, a map to R2. It's a little more subtle if you want to build maps to, to S2 or torus or something. But for the moment, just build a map to R2. What you're going to do is, the simple-minded way is, suppose someone gave you an honest, ordinary handle decomposition of that n manifold. So you would, since it starts with 0 handles, you just start with 0 handle, and then you've got the standard Morse. So you're gonna always, you've got the level sets in between the handles, in between the n-dimensional handles, but in each level set you're going to take a Morse function on it in other directions. You've got 2 Morse functions going in 2 different directions, and so I've got, now suppose I want to attach a handle there. The attaching sphere is some submanifold of this vertical slice, and which I've already built up, and I need to modify my vertical Morse function so that that attaching sphere lies in a level set of that vertical Morse function on this horizontal slice. And so, and I need to do it in such a way that the framing works out. So, for example, if you could build a 4 manifold, you're attaching a 2 handle, you've got a frame not inside a 3 manifold. That 3 manifold, based on what you've done so far, that 3 manifold comes with a vertical Morse function on it. And there we sort of say Hagar splitting, and that knot then runs all around this 3 manifold. You want to modify that Morse function so that that knot lies in a level set in the middle with the right frame. Okay. And of course, so you prove that you can do it. It's not hard, and then the whole Morse 2 function in between those two critical points, those two vertical tangencies, is just the appropriate homotopy G sub t from one Morse function to another, which one Morse function to the appropriate Morse function that has that attaching knot lying in the level set. So let me try to sort of give a sort of example result of an application of this sort of set of ideas. And so, like I said, we know that Rob and I, for the long paper we finished, we talked about in various places which talks about focuses on maps to closed surfaces, 2 spheres, and so on. But the key thing there is that we really prove everything by first proving this is the sort of 2-category type stuff. Really, our techniques are we end up just talking about maps to the square. Okay, and sort of all of our hard work is dealing with maps to the square, which is of course a 2 coordinates between one coordinate between a pair of points. But we say, suppose your 4 manifold is given to you as a 2 coordinates between a 4-dimensional coordinates between 2 3-dimensional coordinates between surfaces, then we can map that to a square, and the work happens there. But I'll go sort of a slightly different direction and just sort of talk about closed 4 manifolds mapping to R2, which some might think is not interesting, but I just want to show a sort of picture. So this is just an example. Oh, the other thing you should wonder about is, suppose you have a Morse 2 function, and it's a map to some surface, and you see all the folds. Let's say it's a 4 manifold mapping down to the surface, and you see all the folds in front of you. So the real question is, what data do you want to write on? What data would you record on the target space that would allow you to recover the 4 manifold and the map and so on? The short answer to that, just for the record, is if you're mapping to, let's say you're mapping to S2, and the fold set, the image of the fold set, these curves, this immersed set of curves in S2 with some cusps, divides the S2 up into regions, and over each region there's some fiber, and if all those regions are simply connected, and all those fibers are genus higher than 1, then all you need to do is sort of indicate as you cross each fold, you draw a little picture of your surface, right? And as you cross each fold, you indicate as you cross each fold in the direction in which it's a 2-fold, these are indebted folds, then you draw what is the attaching circle for that fold. So it's like a lot of little Hagar diagrams sort of patched together. And that determines things. But of course, when you have genus 1 or genus 0, it's much more complicated because of the fact that you can take out a torus across a disk and put it back in a different way, so that screws everything up. Okay, but so suppose you're given a 4 manifold. And it's closed 4 manifold. And suppose you're given a simple closed curve, gamma inside X. I don't know. I'm not saying to say this is just an example construction. We have ideas what it might be useful for, but I shouldn't be too brave and say that itself. Just to throw this out, something you can think about. Then there exists this sort of the data you need to set this up. There exists a Morse 2 function from X to R2 such that, well, I'm just going to show what the image of the fold set looks like. See, I'm just going to draw a big nasty picture here. So it's going to look like all the torus pictures, right? On the outside, the image is going to be at this. And then I'm going to draw this fully general picture, except I have some middle sections that I'll talk about in just a second. And then you're going to have stuff like this. So what's going on? These are, when I put dot dot dots, that means there's any number of parallel folds here. And I put dot dot dots as any number of parallel folds here. I'll tell you what the indices are in just a second. On the other side, you're going to have sort of math order. Let's see. So what are the, and then in the middle, you're going to have, I have never said the word surf graphic here, so I'll say it now. So surf graphic, it's some surf graphic. So surf graphic is just if you take a one parameter family of Morse functions, generic one parameter family between two Morse functions, then it's just the trajectories of the critical points. So in other words, along here, there's a 3 manifold sitting over each vertical slice. That 3 manifold is not going to change, but the critical points are going to move around. You're going to burst to death, so something is going to happen. So what are these folds here? These are index 1 folds up to here. So that means going upwards. Here's a 3 manifold sitting over this vertical slice. There's an index 0 critical point, and then a bunch of index 1 critical points. These are cusps where 1s and 2s are born like that. So this is a 1 and 2s. By the way, if this is a 1 going that way and it's dimension 4, n minus 1 minus 1 is 4 minus 2. So those are index 2 critical points there. So those are index 2 critical points on the vertical 3 manifold. The reason for this funny thing here is that these are 2s going that way, corresponding to the 2 handles of the 4 manifold, right? And so if they're 2s, they become 2, if I think vertically, right, then I've got an index 2 critical point here and an index 1 critical point there. And usually with 3 manifolds, unless you're doing thin position or something, you prefer your 2 handles to be above your 1 handles. So that's the accounts for this funny twist here. So these are again 1s and these are 2s. And so you have, this is just a Morse, and in fact, this 3 manifold is, can you guess what the 3 manifold, you should know what the 3 manifold is, right? From everything I've said. Of course, those who have already told this should be. And this is the test of whether you know what I'm doing. Oh, I haven't told you the index yet. That's why you don't know. That's 1. Those are 1s. So those are going from this way. If you project horizontally, right? This is 0 handle. From this direction, so it's the 4 handle. 4 manifolds, these are the 3 handles. So this vertical slice is connect some of this across S2s. What you get right before the 3 handles. Of course, you could, there's sort of an arbitrary choice. There always is with 4 manifolds, put the 2 handles to the left, right? And then the point is just that. So why do you want all these cusps here, for example? Well, you're looking at your link diagram for your 4 manifold, and there's zillions of crossings. And it doesn't lie in a level set by any means. So you attach your 1 handles, and you get here, you've got connect some of S1 cross S2s after attaching the 1 handles, right? And now in a totally standard vertical Morse function, totally standard Hagar splitting, then you've got this horrendous link with a framed link, which doesn't lie in a level set by any means. And so you've got to stabilize that a lot in order to resolve crossings, put kinks in to get your framings right, and so on. And that's what all these cusps are. These are stabilizations. This is the same 3 manifold from here all the way up to here. We just have a lot of stabilizations, and then you attach your 2 handles like that. So that's just an example of what you can draw. In fact, if you just erase this and change some of the indices, you get the same picture for a 3 manifold, where there's some surf graphic in between. Maybe I'll say something about that in a second. Okay, almost out of time, so I should stop. So maybe I will. What we can do, we can all the fibers are connected. this middle section, the surf graphic, actually completely, you could just draw the surf graphic, and that will completely determine the four manifold and the simple ghost curve gamma and the map to G. We can also make a uniqueness statement, but I definitely don't have time to say that. And sort of the fanciful idea is what can you say about your four manifold? Can you maybe get some invariance by thinking about the surf graphic here, and slides in there, and so on. If you erase this and change your indexing appropriately, you can think of this as, just you have so we're talking about a three manifold domain, right? I claim this is sort of the picture behind ordered Hagar floor diagrams and so on, because you have there's this one paper about factoring. One of their papers has this perspective where you have your standard Hagar splitting over three manifold, right? But then both sides are completely standard. If you go from one to the other, you want to think about vertical Morse function on that Hagar surface, right? And then it's a parameterized Hagar surface, and then you want to get from that parameterization to a different one in order to move in the other side, right? And so there's some surf graphic in there, and they sort of working on sort of organizing invariance based on how what happens step by step across the surf graphic. So I think it's somehow nice